Welcome back. In the last episode, we explored the basics of humidity, what it is, how to read dew point, and how it affects performance. Now let's dive deeper. In this episode, we'll see how humidity drives weather systems, influences stability, and impacts your in-flight decisions. Let's begin with how humidity fuels cloud formation. As moist air rises, it cools. When it reaches its dew point, water vapor condenses into tiny droplets, forming clouds. The type of cloud depends on the rate of ascent, moisture content, and atmospheric stability. If the air is unstable and moisture is abundant, we get cumuliform clouds, fluffy, vertically developed, and often turbulent. If the air is more stable but still moist, we get stratiform clouds, layered, widespread, and usually smoother. Now think about cloud depth. Thicker clouds mean more condensed moisture, potentially more precipitation and turbulence. Thin clouds may be benign or icy. Knowing the cloud type and depth helps you anticipate what's happening inside. Let's connect this to precipitation. As cloud droplets grow, they collide and combine into raindrops or snowflakes. When they're too heavy to stay aloft, they fall as rain, snow, sleet, or hail, depending on temperature. High humidity near the ground also increases the chance of fog and low ceilings. That's why METARs showing temperature and dew point within 1 or 2 degrees Celsius should alert you to possible IFR conditions even if the TAF still shows VFR. Humidity also affects convective weather. Warm, moist air rising rapidly leads to towering cumulonimbus clouds, CBS. These clouds are loaded with moisture, strong updrafts, and instability. That's the formula for thunderstorms. Thunderstorms need 3 things: moisture, instability. Lift humidity supplies the moisture. A front, mountain, or solar heating can provide lift. Instability allows rising air to keep rising. Together, these can form dangerous storm cells. Inside a thunderstorm, moisture fuels violent updrafts. As the air rises and cools, massive amounts of latent heat are released. This intensifies the storm. That's why more humid air can lead to stronger thunderstorms, especially in tropical regions. Let's talk latent heat. When water vapor condenses, it releases hidden energy. This is latent heat. It's a key driver in storm formation and intensity. More moisture equals more energy equals more dangerous weather. Humidity also impacts icing conditions. In the right temperature range, high humidity can cause rapid ice buildup on wings and engine intakes. Even if the air temperature is just above freezing, supercooled droplets can freeze instantly upon contact. This is why flying through moist stratiform clouds between 0 degrees Celsius and -15 degrees Celsius can lead to serious icing, especially at night or when descending through layers. Pilots must know how to recognize and exit these conditions quickly. Let's shift to weather charts. Moisture content isn't always obvious, but clues like dew point spreads, cloud bases, and visibility help. SCUT diagrams and upper air soundings show humidity profiles, key to spotting saturated layers or dry air aloft. Moisture also appears in prog charts, often indicated by frontal boundaries or precipitation zones. If you see a warm front ahead, expect increasing humidity, lower ceilings, and layered cloud development. A cold front often brings convective moisture and abrupt changes. Humidity also varies by region and time of day. Coastal areas often have higher humidity, especially in the morning. Desert air is dry, but moisture can surge during monsoon seasons. Understanding your environment helps anticipate flying conditions. In the tropics, moisture is abundant. That's why clouds build so quickly there, especially in the afternoon. The high humidity and strong sunlight create powerful convection and towering clouds, frequent causes of turbulence and delays. Let's talk tools. Pilots can access humidity forecasts via METARs, TAFs, and satellite imagery. Infrared satellite shows cloud tops, but water vapor imagery reveals moisture aloft even if clouds haven't formed yet. During pre-flight, always note the dew point trend. Is it rising or falling? A rising dew point means increasing humidity. Watch for fog or low ceilings. A falling dew point may signal clearing skies or drier air moving in. In flight, monitor visibility and cloud development. Increasing haze or a sudden rise in cloud bases may suggest moisture building. Use your radar or weather display to track precipitation areas and avoid embedded cells. Let's do a real-world example. You're flying into a coastal airport just after sunset. The temp is 19 degrees Celsius, dew point is 18 degrees Celsius, winds are calm. Expect fog formation, possibly rapidly. Plan for alternate minimums and brief for a missed approach. Also, consider this: at cruise altitude, humidity tends to be low, but just a descent into a moist layer could mean rapid visibility changes, light turbulence, or even ice. Monitor OAT and be ready to adjust anti-ice or request vectors. Let's recap what we've covered. Moisture drives cloud formation, storms, and icing. High humidity equals lower visibility, more fog, more risk. Thunderstorms and stratiform layers form differently, but both require moisture. Tools like dew point, METARs, and satellite help predict humid conditions. Recognizing humidity trends helps you stay ahead of the weather. In the next episode, we'll tackle adiabatics and stability, Part 1. We'll build on everything we've learned about temperature and moisture to understand how the atmosphere reacts to rising and sinking air and what it means for your flight. See you in Meteorology number 16, Adiabatics and Stability, Part 1.